Right, we should be live or not. Why is it showing me as upcoming? Okay, I think it's working now. I think. Need to double check. Coming. Okay, I think it's. Alright. Looks like we are indeed live. Hello. Another practical deep learning stream. I was actually gonna do this stream yesterday, and I actually started doing it, but then my computer, well, actually, to be specific, my internet decided to, well, be annoying, and I could barely get through the video without, some stuttering. And so I just basically decided, you know what, I'm just gonna skip and try again today. So here we are, trying again, part 1.8 of the course. So as you know, there are two parts. We are currently going through the first part. I think, this is the last lesson of part 1. We did part 7 last, was it last Tuesday or last Monday? I feel like it's been forever. Because we did the Kubernetes stuff on Wednesday and Thursday. And then Friday nothing happened on Friday. So it feels like forever ago. And for that reason, I can't say that I truly recollect what we did or what were the highlights of part 7. But I just remember that it wasn't as, I didn't get as much out of it as the other lessons. It's probably my least favorite one, number 7, up to now. Willing to admit that's just skill issues on my part, possibly. But yeah, so last lesson 8, we're gonna go through it. I don't think that we'll jump right into part 2 next week. I think I would like to actually before jumping into part 2, I think what I would like to do is maybe for the rest of this month, just actually do some practical actual hands-on stuff with deep learning. Just experiment with a bunch of tools that are out there. And see what kind of interesting thing we can just, try out. Even if it's just trying out, some open source projects that are released out there, just to get some hands-on hacking, tinkering experience with just understanding the tools that are available out there to build things. I think we are gonna follow up on part 1 by doing some actual hands-on stuff, and then at some point we'll resume with part 2. Because I think part 2 seems like it's more. I want to use the word practical, which is kind of redundant because the course itself is, meant to be practical. But I think at least relative to part 1, part 2 seems like it's more, it's less, and I could be wrong because I'm just looking at the lesson names, and I mean it's denser too, part 2. But yeah, part 2 seems like it's more, you you're likely to get more hands-on. So that's good. Yeah. Anyway, let's just get to it. Let's do part 1.8, part 1, lesson 8, last one. And yeah, let's see. Excuse me.
Now, the other thing we can do...
Oh yeah, this is how far I made it yesterday before. By the time I got to that point, I had to basically start the stream twice. And by then I was like, okay, it's just not happening today. So anyway, let's just start from the beginning here.
So welcome to the last lesson of part 1 of Practical Deep Learning for Coders. It's been a really fun time doing this course, and depending on when you're watching and listening to this, you may want to check the forums or the fast.ai website to see whether we have a part 2 planned, which is going to be sometime towards the end of 2022.
They do.
Or if it's already past that, then maybe there's even a part 2 already on the website. So part 2 goes a lot deeper than part 1, technically, in terms of getting to the point that you should be able to read and implement research papers and deploy models, in a very kind of real life situation. Last lesson we started on the collaborative filtering notebook, and we were looking at collaborative filtering, and this is where we got to, which is creating your own embedding module. And this is a very cool place to start the lesson, because you're going to learn a lot about what's really going on. And it's really important before you dig into this to make sure that you're really comfortable with the 0.5 linear model neural net from scratch notebook. So if parts of this are not totally clear, put it aside and redo this notebook, because what we're looking at from here are kind of the abstractions that PyTorch and FastAI add on top of functionality that we built ourselves from scratch. So if you remember in the neural network from scratch we built, we initialized a number of coefficients, a couple of different layers, and a bias term, and then as the model trained, we updated those coefficients by going through each layer of them and subtracting out the gradients by the learning rate. You probably noticed that in PyTorch we don't have to go to all that trouble, and I wanted to show you how PyTorch does this. PyTorch, we don't have to keep track of what our coefficients or parameters or weights are. PyTorch does that for us, and the way it does that is it looks inside our module, and it tries to find anything that looks like a neural network parameter, or a tensor of neural network parameters, and it keeps track of them. And so here is a class we created called T, which is a subclass of module, and I've created one thing inside it, which is something with the attribute A. So this is A in the T module, and it just contains 3 ones. And so the idea is, maybe we're creating a module, and we're initializing some parameter that we want to train. Now we can find out what trainable parameters, or just what parameters in general, PyTorch knows about in our model by instantiating our model and then asking for the parameters, which you then have to turn that into a list, or in FastCall we have a thing called capital L, which is like a fancy list, which prints out the number of items in the list and shows you those items. Now in this case, when we create our object of type T and ask for its parameters, we get told there are 0 tensors of parameters and a list with nothing in it. Now why is that? We actually said we wanted to create a tensor with 3 ones in it. How would we make those parameters? Well, the answer is that the way you tell PyTorch what your parameters are is you actually just have to put them inside a special object called an nn.parameter. This thing almost doesn't really do anything. In fact, last time I checked, it really quite literally had almost no code in it. Sometimes these things change. Let's take a look. Yeah, okay, so it's about a dozen lines of code or 20 lines of code, which does almost nothing. It's got a way of being copied, it's got a way of printing itself, got a way of saving itself, and it's got a way of being initialized. So a parameter hardly does anything. The key thing is, though, that when PyTorch checks to see which parameters should it update, when it optimizes...
Sorry, I just realized I'm kind of distracted going through something. I think I just need to quickly handle this. Sorry. Just need to read this thing. Well, I'm searching for something that... Oh, you know what? It can wait. Sorry. It can wait. Let's focus.
It just looks for anything that's been wrapped in this parameter class. So if we do exactly the same thing as before, which is to set an attribute containing a tensor with 3 ones in it, but in this case we wrap it in a parameter, we now get told, okay, there's one parameter tensor in this model, and it contains a tensor with 3 ones. And you can see it also actually by default assumes that we're going to require gradient. It's assuming that anything that's a parameter is something that you want to calculate gradients for. Now, most of the time we don't have to do this because PyTorch provides lots of convenient things for us, such as what you've seen before, nn.linear, which is something that also creates a tensor. So this would contain create a tensor of 1 by 3 without a bias term in it. This has not been wrapped in an nn.parameter, but that's okay. PyTorch knows that anything which is basically a layer in a neural net is going to be a parameter, so it automatically considers this a parameter. So here's exactly the same thing again. I construct my object of type T, I've checked for its parameters, and I can see there's one tensor of parameters, and there's our 3 things. And you'll notice that it's also automatically randomly initialize them, which again is generally what we want. So PyTorch does go to some effort to try to make things easy for you. So this attribute A is a linear layer, and it's got a bunch of things in it. One of the things in it is the weights, and that's where you actually find the parameters. That is of type parameter. So a linear layer is something that contains attributes of type parameter. Okay, so what we want to do is we want to create something that works just like this did, which is something that creates a matrix, which will be trained as we train the model. Okay, so an embedding is something which, it's going to create a matrix of this by this. And it will be a parameter, and it's something that, we need to be able to index into, as we did here. And so, what is happening behind the scenes, in PyTorch? It's nice to be able to create these things ourselves.
Okay, so the embedding is a tensor, I'm guessing of rank 2. And so each row represents a user, and the factors represent the columns are, I guess, features. For which we're trying to train a bunch of coefficients. I think that sounds right. All right, just needed to do a gut check on that.
From scratch, because it means we really understand it. And so let's create that exact same module that we did last time. This time we're going to use a function I've created called create params. You pass in a size, so such as, in this case, n uses by n factors. And it's going to call torch.zeros to create a tensor of zeros of the size that you request. And then it's going to do a normal random distribution, so a Gaussian distribution of mean 0, standard deviation 0.01 to randomly initialize those, and it'll put the whole thing into an nn.parameter. So this here is going to create an attribute called user factors, which will be a parameter containing some tensor of normally distributed random numbers of this size. Excuse me. And because it's a parameter, that's going to be stored inside, that's going to be available as in parameters in the module. Oh, I'm sneezing. So user bias will be a vector of parameters. User factors will be a matrix of parameters. Movie factors will be a matrix, n movies by n factors. Movie bias will be a vector of n movies. And this is the same as before. So now in the forward, we can do exactly what we did before. The thing is, when you put a tensor inside a parameter, it has all of the exact same features that a tensor has.
Okay, yeah. User bias is its own, that's the bias term. So it's just one column, and you just need to match the number of rows, I guess, which is in this case n users and n movies, right? Yeah, that sounds right. Wait, so create params. Okay, so it takes in this array of I guess the dimensions, unpacks it to produce a bunch of zeros, and initializes it using a normal distribution when randomly generating the values. So wait, is the table a rank 1 or rank 2 tensor? Jesus, I feel like I should know this off the top of my head. Tensor rank, I think it's rank 2. Okay, yeah, a table is a rank 2, right? Okay, matrix, table matrix. Okay, all right.
So for example, we can index into it. So this whole thing is identical to what we had before. And so that's actually, believe it or not, all that's required to replicate PyTorch's embedding layer from scratch. So that's...
So for the user factors, I'm looking at this here. It's getting... Wait. I mean, these are the rows, right? So it's the first column, all the rows. But then they're using that as a subscript to what's going on there. Sorry. Oh boy. Please don't do this. Oh no. The audio. Hello? Okay. That's better. I'm trying to understand what users... Wait, what is X? Okay, yeah, I have no idea what X is right now. I think that's... Okay. I don't know what X is. And that limits my understanding of what users and movies. I'm trying to picture the shape of what those are supposed to be. Yeah, let's keep going.
Let's run those
for now
and see if it works. And there it is, it's trading. So we'll be able to have a look when this is done at, for example, model dot, let's have a look, movie bias. And here it is, right? It's a parameter containing a bunch of numbers that have been trained. And as we'd expect, it's got 1,665 things in because that's how many movies we have. So a question from Joan and Raphael was, does torch.zeros not produce all zeros? Yes, torch.zeros does produce all zeros. But remember, a method that ends in underscore changes in place the tense it's being applied to. And so if you look up PyTorch normal underscore, you'll see it fills itself with elements sampled from the normal distribution. So this is actually modifying this tensor in place. And so that's why we end up with something just zeros. Now, this is the bit I find really fun, is we train this model, but what did it do? How is it going about predicting who's going to like what movie? Well, one of the things that's happened is we've created this movie bias parameter, which has been optimized. And what we could do is we could find which movie IDs have the highest numbers here and the lowest numbers. So I think it's going to start lowest. And then we can look inside our data loaders and grab the names of those movies for each of those 5 lowest numbers. And what's happened here? Well, we can see, broadly speaking, that it has printed out some pretty crappy movies. And why is that? Well, that's because when it does that matrix product that we saw in the Excel spreadsheet last week, it's trying to figure out who's going to like what movie based on previous movies people have enjoyed or not. And then it adds movie bias, which can be positive or negative. It's a different number for each movie. So in order to do a good job of predicting whether you're going to like a movie or not, it has to know which movies are crap. And so the crap movies are going to end up with a very low movie bias parameter. And so we can actually find out which movies do people, not only which movies do people really not like, but which movies do people like less than one would expect given the kind of movie that it is. So Lawnmower Man 2, for example, not only apparently is it a crappy movie, but based on the kind of movie it is, it's kind of like a high-tech pop kind of sci-fi movie, people who like those kinds of movies still don't like Lawnmower Man 2. So that's what this is meaning. So it's kind of nice that we can use a model not just to predict things, but to understand things about the data. So if we sort by descending, it'll give us the exact opposite. So here are movies that people enjoy, even when they don't normally enjoy that kind of movie. So for example, LA Confidential, classic kind of film noir detective movie with the Aussie Guy Pearce. Even if you don't really like film noir detective movies, you might like this one. Silence of the Lambs, classic kind of, I guess you'd say like horror, kind of, not horror, it's a suspense movie. Even people who don't normally like kind of serial killer suspense movies tend to like this one. Now, the other thing we can do is not just look at what's happening in bias. Oh, by the way, we can do the same thing with users and find out which user just loves movies, even crappy ones, just likes all movies, and vice versa. But what about the other thing? We didn't just have bias, we also had movie factors, which has got the number of movies as one axis and the number of factors as the other, and we passed in 50. What's in that huge matrix? Well, pretty hard to visualize such a huge matrix. And we're not going to talk about the details, but you can do something called PCA, which stands for Principal Component Analysis, and that basically tries to compress those 50 columns down into 3 columns. And then we can draw a chart of the top 2. And so this is PCA component number 1, and this is PCA component number 2. And here's a bunch of movies. And this is a compressed view of these latent factors that it created. And you can see that they obviously have some kind of meaning, right? So over here towards the right, we've got kind of, very pop, mainstream kind of movies. And over here on the left, we've got more of the kind of critically acclaimed, gritty kind of movies. And then towards the top, we've got very kind of action-oriented and sci-fi movies. And then down towards the bottom, we've got very dialogue-driven movies. So remember, we didn't program in any of these things. We don't have any data at all about what movie is what kind of movie. But thanks to the magic of SGD, we just told it to please try and optimize these parameters. And the way it was able to predict who would like what movie was it had to figure out what kinds of movies are there or what kind of taste is there for each movie. So I think that's pretty interesting. So this is called visualizing embeddings. And then this is visualizing the bias. We obviously would rather not do everything by hand, like this, or even like this. And FastAI provides an application for collaborative learner. And so we can create one. And this is going to look much the same as what we just had. We're going to say how many latent factors we want and what the Y range is to do the sigmoid and the multiply. And then we can do fit. And away it goes. So let's see how it does. All right, so it's done a bit better than our manual one. Let's take a look at the model it created. The model looks very similar to what we created in terms of the parameters. You can see these are the 2 embeddings, and these are the 2 biases. And we can do exactly the same thing. We can look in that model, and we can find you'll see it's not called movies, it's items, it's users and items. This is the item bias. So we can look at the item bias, grab the weights, sort, and we get a very similar result. In this case, it's even more confident that LA Confidential is a movie that you should probably try watching, even if you don't like those kind of movies. And Titanic's right out there as well. Even if you don't really like romancy kind of movies, you might like this one. Even if you don't like classic detective, you might like this one. We can have a look at the source code for Colab Loader, and we can see that, let's see, use NN is false by default. So our model is going to be of this type, embedding.bias. So we can take a look at that. Here it is. And look, this does look very similar. Okay, it's creating an embedding using the size we requested for each of users by factors and items by factors and users and items. And then it's grabbing each thing from the embedding in the forward, and it's doing the multiply, and it's adding it up, and it's doing the sigmoid. So yeah, it looks exactly the same. Isn't that neat? So you can see that what's actually happening in real models is not, it's not that weird or magic. So Kurian is asking, is PCA useful in any other areas? And the answer is absolutely. And what I suggest you do, if you're interested, is check out our computational linear algebra course. It's 5 years old now, but this is stuff which hasn't changed for decades, really. And this will teach you all about things like PCA and stuff like that. It's not nearly as directly practical as practical deep learning for coders, but it's definitely very interesting, and it's the kind of thing which, if you want to go deeper, it can become pretty useful later along your path. Okay, so here's something else interesting we can do. Let's grab the movie factors. So that's in our model. It's the item weights, and it's the weight attribute that PyTorch creates. Okay, and now we can convert the movie Silence of the Lambs into its class ID, and we can do that with object to ID, O to I, for the titles. And so that's the movie index of Silence of the Lambs. And what we can do now is we can look through all of the movies in our latent factors and calculate how far apart each vector is, each embedding vector is from this one. And this cosine similarity is very similar to basically the Euclidean distance, the kind of the root sum squared of the differences, but it normalizes it. So basically the angle between the vectors. So this is going to calculate how similar each movie is to the Silence of the Lambs based on these latent factors. And so then we can find which ID is the closest. Yeah, so based on this embedding distance, the closest is dial M for murder, which makes a lot of sense. I'm not going to discuss it today, but in the book, there's also some discussion about what's called the bootstrapping problem, which is the question of if you've got a new company or a new product, how would you get started with making recommendations, given that you don't have any previous history with which to make recommendations? And that's a very interesting problem that you can read about in the book. Now, that's one way to do collaborative filtering, which is where we create that, do that matrix completion exercise using all those dot products. There's a different way, however, which is we can use deep learning. And to do it with deep learning, what we could do is we could basically create our user and item embeddings as per usual. And then we could create a sequential model. So a sequential model is just layers of a deep learning neural network in order. And what we could do is we could just concatenate. So in forward, we could just concatenate the user and item embeddings together, and then do a ReLU. So this is basically a single hidden layer neural network, and then a linear layer at the end to create a single output. So this is a very world's most simple neural net, exactly the same as the style that we created back here in our neural net from scratch. This is exactly the same. But we're using PyTorch's functionality to do it more easily. So in the forward here, we're going to, in the same, exactly the same way as we had before, we'll look up the user embeddings and we'll look up the item embeddings. And then this is new. This is where we concatenate those two things together and put it through our neural network and then finally do our sigmoid. Now, one thing different this time is that we're going to ask FastAI to figure out how big our embeddings should be. And so FastAI has something called get embedding sizes, and it just uses a rule of thumb that says that for 944 users, we recommend 74 factor embeddings, and for 1665 movies, or is it the other way around? I can't remember. We recommend 102 factors for your embeddings. So that's what those sizes are. So now we can create that model, and we can pop it into a learner and fit in the usual way. And so rather than doing all that from scratch, what you can do is you can do exactly the same thing that we've done before, which is to call collaborative learner, but you can pass in the parameter use neural network equals true. And you can then say how big do you want each layer. So this is going to create a 2 hidden layer deep learning neural net. The first will have 1500 and the second will have 50. And then you can say fit, and away it goes. Okay, so here is our, we got 0.87. So these are doing less well than our dot product version, which is not too surprising because kind of the dot product version is really trying to take advantage of our understanding of the problem domain. In practice, nowadays, a lot of companies kind of combine. They kind of create a combined model that has a dot product component and also has a neural net component. The neural net component is particularly helpful if you've got metadata, for example, information about your users, like when did they sign up, how old are they, what sex are they, where are they from, and then those are all things that you could concatenate in with your embeddings, and ditto with metadata about the movie, how old is it, what genre is it, and so forth. All right, so we've got a question from Jonah, which I think is interesting, and the question is there an issue where the bias components are overwhelmingly determined by the non-experts in a genre? In general, actually, there's a more general issue, which is in collaborative filtering recommendation systems, very often a small number of users or a small number of movies overwhelm everybody else. And the classic one is anime. A relatively small number of people watch anime, and those group of people watch a lot of anime. So in movie recommendations, like there's a classic problem, which is every time people try to make a list of well-loved movies, all the top ones seem to be anime. And so you can imagine what's happening in the matrix completion exercise is that there are, some users that just really watch this one genre of movie and they watch an awful lot of them. So in general, you actually do have to be pretty careful about these subtlety kind of issues. I won't go into details about how to deal with them, but they're generally involved in taking various kinds of ratios or normalizing things or so forth. All right, so that's collaborative filtering. And I wanted to show you something interesting then about embeddings, which is that embeddings are not just for collaborative filtering. And in fact, if you've heard about embeddings before, you've probably heard about them in the context of natural language processing.
Yeah.
So you might have been wondering, back when we did the Hugging Face Transformers stuff, how did we go about using text as inputs to models? And we talked about how you can turn words into integers. We make a list. So here's the movie. Here's the poem. I am Sam. I am Daniel. I am Sam. Sam. I am. That's Sam. I am. Etc. Etc. We can find a list of all the unique words in the poem and make this list here. And then we can give each of those words a unique ID, just arbitrarily. Well, in this case, it's alphabetical order, but it doesn't have to be. And so we kind of talked about that. And that's what we do with categories in general. But how do we turn those into lists of random numbers? And you might not be surprised to hear what we do is we create an embedding matrix. So here's an embedding matrix containing 4 latent factors for each word in the vocab. So here's each word in the vocab, and here's the embedding matrix. So if we then want to present this poem to a neural net, then what we do is we list out our poem. I do not like that Sam I am. Do you like green eggs and ham, etc. Then for each word, we look it up. So in Excel, for example, we use match. So that will find this word over here and find it is word ID 8. And then we will find the 8th word and the first embedding. And so that gives us, that's not right, 8. Oh, no, that's right. Sorry, here it is. It's just a weird column. That's going to be 0.22, then 0.1, 0.01, here it is 0.22, 0.1, etc. So this is the embedding matrix we end up with for this poem. And so if you wanted to train or use and train neural network on this poem, you basically turn it into this matrix of numbers. And so this is what an embedding matrix looks like in an NLP model, and it works exactly the same way, as you can see. And then you can do exactly the same things in terms of interpretation of an NLP model by looking at both the bias factors and the latent factors in a word embedding matrix. So hopefully you're getting the idea here that our different models, the inputs to them, they're based on a relatively small number of kind of basic principles. And these principles are generally things like look up something in an array. And then we know inside the model, we're basically multiplying things together, adding them up, and replacing the negatives with zeros. So hopefully you're getting the idea that what's going on inside a neural network is generally not that complicated. But it happens very quickly and at scale. Now, it's not just collaborative filtering and NLP, but also tabular analysis. So in chapter 9 of the book, we've talked about how random forests can be used for this, which was for, this is for the thing where we're predicting the auction sale price of industrial heavy equipment like bulldozers. Instead of using a random forest, we can use a neural net. Now, in this data set, there are some continuous columns, and there are some categorical columns. Now, I'm not going to go into the details too much, but in short, we can separate out the continuous column and categorical columns using concat split, and that will automatically find which is which based on the data types. And so in this case, it looks like, okay, so continuous columns, the elapsed sale date. So I think it's the number of seconds or years or something since the start of the data set is a continuous variable. And then here are the categorical variables. So for example, there are 6 different product sizes and 2 coupler systems, 5,059 model descriptions, 6 enclosures, 17 tire sizes, and so forth. So we can use fast AI basically to say, okay, we'll take that data frame and pass in the categorical and continuous variables and create some random splits. And what's the dependent variable? And we can create data loaders from that. And from that, we can create a tabular learner. And basically what that's going to do is it's going to create a pretty regular multi-layer neural network, not that different to this one that we created by hand. And each of the categorical variables, it's going to create an embedding for it. And so I can actually show you this, right? So we're going to use tabular learner to create the learner. And so tabular learner is 1, 2, 3, 4, 5, 6, 7, 8, 9 lines of code. And basically the main thing it does is create a tabular model. And so then tabular model, you're not going to understand all of it, but you might be surprised at how much. So a tabular model is a module. We're going to be passing in how big is each embedding going to be. And tabular learner, what's that passing in? It's going to call get embedding sizes, just like we did manually before, automatically. So that's how it gets its embedding sizes. And then it's going to create an embedding for each of those embedding sizes, from number of inputs to number of factors. Dropout we're going to come back to later. Batch norm we won't do till part 2. So then it's going to create a layer for each of the layers we want, which is going to contain a linear layer followed by batch norm followed by dropout. It's going to add the sigmoid range we've talked about at the very end. And so the forward, this is the entire thing. If there's some embeddings, it'll go through and get each of the embeddings using the same indexing approach we've used before. It'll concatenate them all together. And then it'll run it through the layers of the neural net, which are these. So yeah, we don't know all of those details yet, but we know quite a few of them. So that's encouraging, hopefully. And once we've got that, we can do the standard LR find and fit. Now, this exact data set was used in a Kaggle competition. This data set was in a Kaggle competition. And the third place getter published a paper about their technique. It's basically almost the exact one I'm showing you here. So it wasn't this data set. It was a data set. It was a different one. It was about predicting the amount of sales in different stores. But they used this basic kind of technique. And one of the interesting things is that they used a lot less manual feature engineering than the other high-placed entries. Like they had a much simpler approach. And one of the interesting things, they published a paper about their approach. So they published a paper about their approach. So this is the team from this company. And they basically describe here exactly what I just showed you, these different embedding layers being concatenated together and then going through a couple of layers of a neural network. And it's showing here, it points out in the paper exactly what we learned in the last lesson, which is embedding layers are exactly equivalent to linear layers on top of a one-hot encoded input. Yeah, they found that their technique worked really well. One of the interesting things they also showed is that you can create your neural net, get your trained embeddings, and then you can put those embeddings into a random forest or gradient boosted tree, and your mean average percent error will dramatically improve. So you can actually combine random forests and embeddings, or gradient boosted trees and embeddings, which is really interesting. Now, what I really wanted to show you, though, is what they then did. So as I said, this was a thing about the predicted amount that different products would sell for at different shops around Germany. And what they did was they had, so one of their embedding matrices was embeddings by region. And then they did, I think this is a PCA, principal component analysis, of the embeddings for their German regions. And when they create a chart of them, you can see that the locations that are close together in the embedding matrix are the same locations that are close together in Germany. So you can see here's the blue ones, and here's the blue ones. And again, it's important to recognize that the data that they used had no information about the location of these places. The fact that they are close together geographically is something that was figured out as being something that actually helped it to predict sales. And so in fact, they then did a plot showing each of these dots is a shop, a store. And it's showing for each pair of stores, how far away is it in real life, in metric space, and then how far away is it in embedding space. And there's this very strong correlation, right? So it's kind of reconstructed somehow, this kind of the geography of Germany by figuring out how people shop. And similar for days of the week. So there was no information really about days of the week, but when they put it on the embedding matrix, the days of the week, Monday, Tuesday, Wednesday close to each other, Thursday, Friday close to each other, as you can see, Saturday and Sunday close to each other, and ditto for months of the year, January, February, March, April, May, June. So yeah, really interesting, cool stuff, I think. What's actually going on inside a neural network. All right, let's take a 10-minute break, and I will see you back here at 7:10. All right, folks, this is something I think is really fun, which is we've looked at what goes into the start of a model, the input. We've learned about how they can be categories or embeddings, and embeddings are basically kind of one-hot encoded categories with a little compute trick, or they can just be continuous numbers. We've learned about what comes out the other side, which is a bunch of activations, so just a bunch of tensor of numbers, which we can use things like softmax to constrain them to add up to 1, and so forth. And we've looked at what can go in the middle, which is the matrix multipliers, sandwiched together with as rectified linear units. And I mentioned that there are other things that can go in the middle as well, but we haven't really talked about what those other things are. So I thought we might look at one of the most important and interesting version of things that can go in the middle. But what you'll see is it turns out it's actually just another kind of matrix multiplication. which might not be obvious at first, but I'll explain. We're going to look at something called a convolution. And convolutions are at the heart of a convolutional neural network. So the first thing to realize is a convolutional neural network is very, very, very similar to the neural networks we've seen so far. It's got inputs, it's got things that are a lot like, or actually are a form of matrix multiplication, sandwiched with activation functions, which can be rectified linear. But there's a particular thing which makes them very useful for computer vision. And I'm going to show you using this Excel spreadsheet that's in our repo called convexample. And we're going to look at it using an image from MNIST. So MNIST is kind of the world's most famous computer vision data set, I think, because it was like the first one really which really showed image recognition being cracked. It's pretty small by today's standards. It's a data set of handwritten digits. Each one is 28 by 28 pixels. But back in the mid-90s, Jan LeCun showed really practically useful performance on this data set, and as a result ended up with convnets being used in the American banking system for reading checks. So here's an example of one of those digits. This is a 7 that somebody drew. It's one of those ones with a stroke through it. And this is what it looks like. This is the image. And so I got it from, this is just one of the images from MNIST, which I put into Excel. And what you see in the next column is a version of the image where the horizontal lines are being recognized, and another one where the vertical lines are being recognized. And if you think back to that Zeiler and Fergus paper that talked about what the layers of a neural net does, this is absolutely an example of something that we know that the first layer of a neural network tends to learn how to do. Now, how did I do this? I did this using something called a convolution. And so what we're going to do now is we're going to zoom in to this Excel notebook. We're going to keep zooming in. We're going to keep zooming in. So take a look, keep an eye on this image, and you'll see that once we zoom in enough, it's actually just made of numbers, which, as we discussed in the very first lesson, we saw how images are made of numbers. So here they are, right? Here are the numbers between 0 and 1. And what I just did is I just used a little trick. I used Microsoft Excel's conditional formatting to basically make things, the higher numbers, more red. So that's how I turned this Excel sheet. And I've just rounded it off to the nearest decimal, but it's actually bigger than that. So here is the image as numbers. And so let me show you how we went about creating this top edge detector. What we did was we created this formula. Don't worry about the max. Let's focus on this. What it's doing is have a look at the colored in areas. It's taking each of these cells and multiplying them by each of these cells, and then adding them up. And then we do the rectified linear part, which is if that ends up less than 0, then make it 0. So this is like a rectified linear unit, but it's not doing the normal matrix product. It's doing the equivalent of a dot product, but just on these 9 cells and with just these 9 weights. So you might not be surprised to hear that if I move now 1 to the right, then now it's using the next 9 cells. Right? So if I move like to the right quite a bit and down quite a bit to here, it's using these 9 cells. So it's still doing a dot product, right, which as we know is a form of matrix multiplication. But it's doing it in this way where it's kind of taking advantage of the geometry of the situation, that the things that are close to each other are being multiplied by this consistent group with the same 9 weights each time. Because there's actually 28 by 28 numbers here, right, which I think is 768. 28 times 28, plus enough, 784. But we don't have 784 parameters, we only have 9 parameters. And so this is called a convolution. So a convolution is where you basically slide this kind of little 3 by 3 matrix across a bigger matrix, and at each location you do a dot product of the corresponding elements of that 3 by 3 with the corresponding elements of this 3 by 3 matrix of coefficients. Now, why does that create something that finds, as you see, top edges? Well, it's because of the particular way I constructed this 3 by 3 matrix. What I said was that all of the rows just above, so these ones, are going to get a 1, and all of the ones just below are going to get a -1, and all of the ones in the middle are going to get a 0. So let's think about what happens somewhere like here, right? That is, let's try to find the right one. Here it is. So here we're going to get 1 times 1 plus 1 times 1 plus 1 times 1 minus 1 times 1 minus 1 times 1 minus 1 times 1. We're going to get 0. But what about up here? Here we're going to get 1 times 1 plus 1 times 1 plus 1 times 1. These do nothing because they're times 0 minus 1 times 0. So we're going to get 3. So we're only going to get 3, the highest possible number, in the situation where these are all as black as possible, or in this case as red as possible, and these are all white. And so that's only going to happen at a horizontal edge. So the one underneath it does exactly the same thing, exactly the same formulas. Oopsie daisy. The one underneath are exactly the same formulas. A 3 by 3 sliding thing here, but this time we've got a different little mini matrix of coefficients, which is all 1s going down and all -1s going down. And so for exactly the same reason, this will only be 3 in situations where they're all 1 here and they're all 0 here. So you can think of a convolution as being a sliding window of little mini dot products of these little 3 by 3 matrices. And they don't have to be 3 by 3, right? We could have just basically done 5 by 5, and then we'd have a 5 by 5 matrix of coefficients, or whatever size you like. So the size of this is called its kernel size. This is a 3 by 3 kernel for this convolution. So then, because this is deep learning, we just repeat these steps again and again and again. So this layer I'm calling conv1, it's the first convolutional layer. So conv2 is going to be a little bit different, because on conv1 we only had a single channel input. It's just black and white, or black and white grayscale, one channel. But now we've got 2 channels. We've got the make it a little smaller so we can see better. We've got the horizontal edges channel and the vertical edges channel. And we have a similar thing in the first layer of its color. We have a red channel, a green channel, and a blue channel. So now our filter, this is called the filter, this little mini matrix is called the filter. Our filter now contains a 3 by 3 by depth 2, or if you want to think another way, 2 3x3 kernels, or 1 3x3x2 kernel. And we basically do exactly the same thing, which is we're going to multiply each of these by each of these and sum them up. But then we do it for the second bit as well. We multiply each of these by each of these and sum them up. And so that gives us, I think I just picked some random numbers here, right? So this is going to now be something which can combine, the second set, so it's, each of the red ones by each of the blue ones, that's here, plus each of the green ones times each of the mauve ones, that's here. So this first filter is being applied to the horizontal edge detector, and the second filter is being applied to the vertical edge detector. And as a result, we can end up with something that combines features of the two things. And so then we can have a second channel over here, which is just a different bunch of convolutions for each of the two channels, this one times this one. Again, you can see the colors. So what we could do is, if once we kind of get to the end, we'll end up, as I'll show you how in a moment, we'll end up with a single set of 10 activations, one per digit we're recognizing, 0 to 9. Or in this case, I think we could just create one, maybe we're just trying to recognize nothing but the number 7, or not the number 7, so we could just have one activation. And then we would backpropagate through this using SGD in the usual way, and that is going to end up optimizing these numbers. So in this case, I manually put in the numbers I knew would create edge detectors. In real life, you start with random numbers, and then you use SGD to optimize these parameters. Okay, so there's a few things we can do next, and I'm going to show you the way that was more common a few years ago, and then I'll explain some changes that have been made more recently. What happened a few years ago was we would then take these activations, which as you can see, these activations now are kind of in a grid pattern, and we would do something called max pooling. And max pooling is kind of like a convolution, it's a sliding window, but this time as the sliding window goes across, so here up to here, we don't do a dot product over a filter, but instead we just take a maximum. See here, this is the maximum of these four numbers. And if we go across a little bit, this is the maximum of these four numbers. Go across a bit, and so forth. Oh, that goes off the edge. And you can see what happens when this is called a 2 by 2 max pooling. So you can see what happens with a 2 by 2 max pooling. We end up losing half of our activations on each dimension. So we're going to end up with only 1/4 of the number of activations we used to have. And that's actually a good thing, because if we keep on doing convolution, max pool, we're going to get fewer and fewer and fewer activations until eventually we'll just have one left, which is what we want. That's effectively what we used to do, but the other thing I mentioned is we didn't normally keep going until there's only one left. What we used to then do is we basically say, okay, at some point we're going to take all of the activations that are left, and we're going to basically just do a dot product of those with a bunch of coefficients, not as a convolution, but just as a normal linear layer, and this is called the dense layer. And then we would add them all up, so we basically end up with our final big dot product of all of the max pooled activations by all of the weights, and we'd do that for each channel, and so that would give us our final activation. And as I say here, and this would actually have 10 activations, so you'd have a separate set of weights for each of the digits you're predicting, and then softmax after that. Okay, nowadays we do things very slightly differently. Nowadays we normally don't have max pool layers, but instead, what we normally do is when we do our sliding window, like this one here, we don't normally, let's go back to C. So when I go 1 to the right, so currently we're starting in cell column G. If I go 1 to the right, the next one is column H. And if I go 1 to the right, the next one starts in column I. So you can see it's sliding the window every 3 by 3. Nowadays, what we tend to do instead is we generally skip one. So we would normally only look at every second. So we would, after doing column I, we would skip columns J and we'd go straight to column K. And that's called a stride 2 convolution. We do that both across the rows and down the columns. And what that means is every time we do a convolution, we reduce our effective kind of feature size, grid size, by 2 on each axis. So it reduces it by 4 in total. So that's basically instead of doing max pooling. And then the other thing that we do differently is nowadays we don't normally have a single dense layer at the end, a single matrix multiplier at the end. But instead what we do, we generally keep doing stride 2 convolutions. So each one's going to reduce the grid size by 2 by 2. We keep going down until we've got about a 7 by 7 grid. And then we do a single pooling at the end. And we don't normally do max pool nowadays. Instead we do an average pool. So we average the activations of each one of the 7 by 7 features. This is actually quite important to know, because if you think about what that means, it means that something like an ImageNet style image detector is going to end up with a 7 by 7 grid. Let's try to say, is this a bear? And in each of the parts of the 7 by 7 grid, it's basically saying, is there a bear in this part of the photo? Is there a bear in this part of the photo? Is there a bear in this part of the photo? And then it takes the average of those 49 7 by 7 predictions to decide whether there's a bear in the photo. That works very well if it's basically a photo of a bear, right? Because most, if the bear is big and takes up most of the frame, then most of those 7 by 7 bits are bits of a bear. On the other hand, if it's a teeny tiny bear in the corner, then potentially only one of those 49 squares has a bear in it. And even worse, if it's like a picture of lots and lots of different things, only one of which is a bear. It could end up not being a great bear detector. And so this is where the details of how we construct our model turn out to be important. And so if you're trying to find just one part of a photo that has a small bear in it, you might decide to use maximum pooling instead of average pooling. Because max pooling will just say, I think this is a picture of a bear if any one of those 49 bits of my grid has something that looks like a bear in it. So these are potentially important details which often get hand-waved over. Although, again, the key thing here is that this is happening right at the very end, right? That max pool, that average pool. And actually, FastAI handles this for you. We do a special thing which we kind of independently invented. I think we did it first, which is we do both max pool and average pool, and we concatenate them together. We call that concat pooling, and that has since been reinvented in at least one paper. And so that means that you don't have to think too much about it, because we're going to try both for you, basically. So I mentioned that this is actually really just matrix multiplication. And to show you that, I'm going to show you some images created by a guy called Matthew Kleinsmith, who did this actually, I think this was in our very first ever course, might have been part 2 course. And he basically pointed out that in a certain way of thinking about it, it turns out that a convolution is the same thing as a matrix multiply. So I want to show you how he shows this. He basically says, okay, let's take this 3x3 image and a 2x2 kernel containing the coefficients alpha, beta, gamma, delta. And so in this, as we slide the window over, each of the colors are multiplied together. Red by red, plus green by green, plus, what is that, orange by orange, plus blue by blue, gives you this. And so put it another way, algebraically, P equals alpha times A plus beta times B, etc. And so then as we slide to this part, we're multiplying, again, red by red, green by green, so forth. So we can say Q equals alpha times B plus beta times C, etc. And so this is how we calculate a convolution using the approach we just described as a sliding window. But here's another way of thinking about it. We could say, okay, we've got all these different things, A, B, C, D, E, F, G, H, J. Let's put them all into a single vector. And then let's create a single matrix that has alpha, 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 beta, 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 etc. And then if we do this matrix multiplied by this vector, we get this, with these grey zeros in the appropriate places, which gives us this, which is the same as this. And so this shows that a convolution is actually a special kind of matrix multiplication. It's a matrix multiplication where there are some zeros that are fixed and some numbers that are forced to be the same. Now in practice, it's going to be faster to do it this way, but it's a useful kind of thing to think about, I think, that just to realize, like, oh, it's just another of these special types of matrix multiplications. Okay, I think, well, let's look at one more thing. Because there was one other thing that we saw, and I mentioned we would look at in the tabular model, which is called dropout. And I actually have this in my Excel spreadsheet. If you go to the conv example dropout page, you'll see we've actually got a little bit more stuff here. We've got the same input as before, and the same first convolution as before, and the same second convolution as before. And then we've got a bunch of random numbers. They're showing as between 0 and 1, but they're actually, that's just because they're rounding off, they're actually random numbers between, you know, the floats between 0 and 1. Over here, we're then saying if, let's have a look. So way up here, I'll zoom in a bit, I've got a dropout factor. Let's change this to 0.5. There we go. So over here, this is something that says if the random number in the equivalent place is greater than 0.5, then 1, otherwise 0. And so here's a whole bunch of 1s and 0s. Now this thing here is called a dropout mask. Now what happens is we multiply over here, we multiply the dropout mask, and we multiply it by our filtered image. And what that means is we end up with exactly the same image we started with. Here's the image we started with, but it's corrupted. Random bits of it have been deleted. And based on the amount of dropout we use, so if we change it to say 0.2, not very much of it's deleted at all, so it's still very easy to recognize. Whereas if we use lots of dropout, say 0.8, it's almost impossible to see what the number was. And then we use this as the input to the next layer. So that seems weird. Why would we delete some data at random from our processed image, from our activations after a layer of convolutions? Well, the reason is that a human is able to look at this corrupted image and still recognize it's a 7. And the idea is that a computer should be able to as well. And if we randomly delete different bits of the activations each time, then the computer is forced to learn the underlying real representation rather than overfitting. You can think of this as data augmentation, but it's data augmentation not for the inputs, but data augmentation for the activations. So this is called a dropout layer. And so dropout layers are really helpful for avoiding overfitting. And you can decide how much you want to compromise between good generalization, so good, avoiding overfitting, versus getting something that works really well on the training data. And so the more dropout you use, the less good it's going to be on the training data, but the better it ought to generalize. And so this comes from a paper by Jeffrey Hinton's group quite a few years ago now. Rustin's now at Apple, I think. And then Kajeski and Hinton went on to found Google Brain. And you can see here they've got this picture of a fully connected neural network, 2 layers, just like the one we built. And here, look, they're kind of randomly deleting some of the activations, and all that's left is these connections. And so there's a different bunch that's going to be deleted each batch. I think this is an interesting point. So dropout, which is super important, was actually developed in a master's thesis, and it was rejected from the main neural networks conference, then called NIPS, now called NeurIPS. So it ended up being disseminated through Archive, which is a preprint server. And as it's just been pointed out on our chat, that Ilya was one of the founders of OpenAI. I don't know what happened to Nitish. I think he went to Google Brain as well, maybe. Yeah, so peer review is a very fallible thing in both directions. And it's great that we have preprint servers so we can read stuff like this, even if reviewers decide it's not worthy. It's been one of the most important papers ever. Okay, now I think that's given us a good tour now. We've really seen quite a few ways of dealing with input to a neural network. Quite a few things can happen in the middle of a neural network. We've only talked about rectified linear units, which is this one here, 0 if x is less than 0 or x otherwise. These are some of the other activations you can use. Don't use this one, of course, because you end up with a linear model, but they're all just different functions. I should mention, like, it turns out these don't matter very much. Basically, pretty much any nonlinearity works fine. So we don't spend much time talking about activation functions, even in part 2 of the course, just a little bit. So yeah, so we understand there are There's our inputs. They can be one-hot encoded, or embeddings, which is a computational shortcut. There are sandwich layers of matrix multipliers and activation functions. The matrix multipliers can sometimes be special cases, such as the convolutions or the embeddings. The output can go through some tweaking, such as the softmax. And then, of course, you've got the loss function, such as cross-entropy loss or mean squared error or mean absolute error. But, it's not, there's nothing too crazy going on in there. So I feel like we've got a good sense now of like what goes inside, a wide range of neural nets. You're not going to see anything too weird from here. And we've also seen a wide range of applications. So before you come back to do part 2, what now? And we're going to have a little AMA session here. And in fact, one of the questions was, what now? So this is quite good. One thing I strongly suggest is if you've got this far, it's probably worth you investing your time in reading Radek's book, which is meta-learning. And so meta-learning is very heavily based on the kind of teachings of FastAI over the last few years, and it's all about how to learn deep learning and learn pretty much anything. Because you've got to this point, you may as well know how to get to the next point as well as possible. And the main thing you'll see that Radek talks about, or one of the main things, is practicing and writing. So if you've kind of zipped through the videos on 2x and haven't done any exercises, go back and watch the videos again. A lot of the best students end up watching them 2 or 3 times, probably more like 3 times, and actually go through and code as you watch, and experiment. Write blog posts about what you're doing. Spend time on the forum, both helping others and seeing other people's answers to questions. Read the success stories on the forum and of people's projects to get inspiration for things you could try. One of the most important things to do is to get together with other people. For example, you can do a Zoom study group. In fact, on our Discord, which you can find through our forum, there's always study groups going on, or you can create your own. A study group to go through the book together. And of course, build stuff. And sometimes it's tricky to always be able to build stuff for work because maybe you're not quite in the right area, or they're not quite ready to try out deep learning yet. But that's okay. Build some hobby projects. Build some stuff just for fun, or build some stuff that you're passionate about. So it's really important to not just put the videos away and go away and do something else, because you'll forget everything you've learned and you won't have practiced. So one of our community members went on to create an activation function, for example, which is Mish, which is now, as Tanishka's just reminded me on our forums, is now used in many of the state-of-the-art networks around the world, which is pretty cool. And he's now at Mila, I think, one of the top research labs in the world. I wonder how that's doing. Let's have a look. Go to Google Scholar. Nice, 486 citations. They're doing great. All right, let's have a look at how our AMA topic is going and pick out some of the highest ranked AMAs. Okay. So the first one is from Lucas, and actually maybe I should, let's switch our view here. So our first AMA is from Lucas, and Lucas asks, how do you stay motivated? I often find myself overwhelmed in this field. There are so many new things coming up that I feel like I have to put so much energy just to keep my head above the waterline. That's a very interesting question. I mean, I think, Lucas, that the important thing is to realize you don't have to know everything. In fact, nobody knows everything, and that's okay. What people do is they take an interest in some area, and they follow that, and they try and do the best job they can of keeping up with some little sub area. And if a little sub area is too much to keep up on, pick a sub area. There's no need for it to be demotivating that there's a lot of people doing a lot of interesting work in a lot of different subfields. That's cool. It used to be kind of dull with, there's only basically 5 labs in the world working on neural nets. And from time to time, take a dip into other areas that maybe you're not following as closely. But when you're just starting out, you'll find that things are not changing that fast at all, really. It can kind of look that way because people are always putting out press releases about their new tweaks. But fundamentally, the stuff that is in the course now is not that different to what was in the course 5 years ago. The foundations haven't changed. And it's not that different, in fact, to the convolutional neural network that Jan LeCun used on MNIST back in 1996. It's, the basic ideas I've described are forever. The way the inputs work and the sandwiches of matrix multipliers and activation functions and the stuff you do to the final layer. Everything else is tweaks. And the more you learn about those basic ideas, the more you'll recognize those tweaks as simple little tweaks that you'll be able to quickly get your head around. So then Lucas goes on to comment, another thing that constantly bothers me is I feel the field is getting more and more skewed towards bigger and more computationally expensive models, and huge amounts of data. I keep wondering if, in some years from now, I would still be able to train reasonable models with a single GPU, or if everything is going to require a compute cluster. It's a great question. I get that a lot. But interestingly, I've been teaching people machine learning and data science stuff for nearly 30 years. And I've had a variation of this question throughout. And the reason is that...
It's been 3 years, and here we are, and OpenAI and a bunch of other folks are getting together to build a $500 billion Stargate project. So, but at the same time, you can get a reasonably good AI model running locally on your MacBook or your, custom built PC. So, I think it's going both directions, really. There is work being done so that, um, you can get quality stuff on both ends. Uh, Local, um, small to moderate compute versus, hyper scalar compute.
Engineers always want to push the envelope in like on the biggest computers they can find. That's just this like fun thing engineers love to do. And by definition, they're going to get slightly better results than people doing exactly the same thing on smaller computers. So it always looks like, oh, you need big computers to be state of the art. But that's actually never true, right? Because there's always smarter ways to do things, not just bigger ways to do things. And so, when you look at Fast AI's Dawnbench success, when we trained ImageNet faster than anybody had trained it before on standard GPUs, me and a bunch of students, that was not meant to happen. Google was working very hard with their TPU introduction to try to show how good they were. Intel was using like 256 PCs in parallel or something. But yeah, we used common sense and smarts and showed what can be done. It's also a case of picking the problems you solve. So I would not be probably doing like going head to head up against codecs and trying to create code from English descriptions. Because that's a problem that does probably require very large neural nets and very large amounts of data. But if you pick areas in different domains, there's still huge areas where much smaller models are still going to be state of the art. So hopefully that helped answer your question. Let's see what else we've got here. So Daniel has obviously been following my journey with teaching my daughter math. So I homeschool my daughter. And Daniel asks, how do you homeschool young children, science in general and math in particular? Would you share your experiences by blogging or in lectures someday? Yeah, I could do that. So I actually spent quite a few months just reading research papers about education recently. So I do probably have a lot I probably need to talk about at some stage. But yeah, broadly speaking, I lean into using computers and tablets a lot more than most people, because actually there's an awful lot of really great apps that are super compelling. They're adaptive, so they go at the right speed for the student, and they're fun. And I really like my daughter to have fun. I really don't like to force her to do things. For example, there's a really cool app called DragonBox Algebra 5 Plus, which teaches algebra to 5-year-olds by using a really fun computer game involving helping dragon eggs to hatch. And it turns out that, yeah, algebra, the basic ideas of algebra are no more complex than the basic ideas that we do in other kindergarten math. And all the parents I know of who have given their kids DragonBox Algebra 5 Plus, their kids have successfully learned algebra. So that would be an example. But yeah, we should talk about this more at some point.
DragonBox. I should look that
All
up.
right. Let's see what else we've got here. So Farah says, the walkthroughs have been a game changer for me. The knowledge and tips you shared in those sessions are skills required to become an effective machine learning practitioner and utilize Fast AI more effectively. Have you considered making the walkthroughs a more formal part of the course, doing a separate software engineering course, or continuing live coding sessions between part 1 and 2? So yes, I am going to keep doing live coding sessions. At the moment, we've switched to those specifically to focusing on APL. And then in a couple of weeks, they're going to be going to Fast AI study groups. And then after that, they'll gradually turn back into more live coding sessions. But yeah, the thing I try to do in my live coding or study groups or whatever is, yeah, definitely try to show the foundational techniques that just make life easier as a coder or a data scientist. When I say foundational, I mean, yeah, the stuff which you can reuse again and again and again, like learning regular expressions really well, or knowing how to use a VM, or understanding how to use the terminal and command line, all that kind of stuff. Never goes out of style, never gets old. And yeah, I do plan to, at some point, hopefully actually do a course really all about that stuff specifically. But yeah, for now, the best approach is follow along with live coding and stuff. Okay, WG Pubs, which is Wade, asks, how do you turn a model into a business? Specifically, how does a coder with little or no startup experience turn an ML-based Gradio prototype into a legitimate business venture? Okay, I plan to do a course about this at some point as well. So, obviously there isn't a 2-minute version to this, but the key thing with creating a legitimate business venture is to solve a legitimate problem, a problem that people need solving and which they will pay you to solve. And so it's important not to start with your fun Gradio prototype as the basis of your business, but instead start with, here's a problem I want to solve. And generally speaking, you should try to pick a problem that you understand better than most people. So it's either a problem that you face day to day in your work, or in some hobby or passion that you have, or that your club has, or your local school has, or your spouse deals with in their workplace. It's something where you understand that there's something that doesn't work as well as it ought to. Particularly something where you think to yourself, if they just used deep learning here, or some algorithm here, or some better compute here, that problem would go away. And that's the start of a business. And so then my friend Eric Ries wrote a book called The Lean Startup, where he describes what you do next, which is basically you fake it. You create, so he calls it the minimum viable product. You create something that solves that problem, that takes as little time as possible to create. It could be very manual, it can be loss-making, it's fine. Even the bit in the middle where you're like, oh, there's going to be a neural net here, it's fine to launch without the neural net and do everything by hand. You're just trying to find out if people are going to pay for this, and is this actually useful? And then once you have hopefully confirmed that the need is real, that people will pay for it, and you can solve the need, you can gradually make it less and less of a fake, and do more and more getting the product where you want it to be. Okay, I don't know how to pronounce the name MIWOJC. MIWOJC says, Jeremy, can you share some of your productivity hacks from the content you produce? It may seem you work 24 hours a day. Okay, I certainly don't do that. I think one of my main productivity hacks actually is not to work too hard, or at least, no, not to work too hard, not to work too much. I spend probably less hours a day working than most people, I would guess. But I think I do a couple of things differently when I'm working. One is I've spent at least half of every working day since I was about 18, learning or practicing something new. Could be a new language, could be a new algorithm, could be something I read about. And nearly all of that time, therefore, I've been doing that thing more slowly than I would if I just used something I already knew. Which often drives my coworkers crazy because they're like, why aren't you focusing on getting that thing done? But in the other 50% of the time, I'm constantly, building up this kind of exponentially improving base of expertise in a wide range of areas. And so now I do find, I can do things often orders of magnitude faster than people around me, or certainly many multiples faster than people around me, because I, know a whole bunch of tools and skills and ideas which, other people don't necessarily know. So I think that's one thing that's been helpful. And then another is, try to really not overdo things, like get good sleep and eat well and exercise well. And also I think it's a case of like
Easier said than
tenacity.
done.
I've noticed a lot of people give up much earlier than I do. So yeah, if you
The sleep part.
if you just keep going until something's actually finished,
It's rough for me.
then that's going to put you in a small minority, to be honest. Most people don't do that. When I say finish, like finish something really nicely. And I try to make it like, so I particularly like coding, and so I try to do a lot of coding related stuff. So I create things like NBDev, and NBDev makes it much, much easier for me to finish something nicely, So in my kind of chosen area, I've spent quite a bit of time trying to make sure it's really easy for me to like get out a blog post, get out a Python library, get out a notebook analysis, whatever. So yeah, trying to make these things I want to do easier, and so then I'll do them more. So, well, thank you, everybody. That's been a lot of fun. Really appreciate you taking the time to go through this course with me. If you enjoyed it, it would really help if you would give a like on YouTube, because it really helps other people find the course, goes into the YouTube recommendation system. And please do come and help other beginners on forums.fast.ai. It's a great way to learn yourself, is to try to teach other people. And I hope you'll join us in part 2. Thanks everybody very much. I've really enjoyed this process, and I hope I get to meet more of you in person in the future. Bye.
All right, we made it.
Hi.
Barely. I was losing steam, I think, halfway through the lecture there. That was not great, but the next couple of sessions following up on this will be more hands-on, so it won't just be me watching the lecture, and I think that would be a good way to go. A good way to work on some muscle memory for just getting practical with working on practical projects, or trying out some stuff before we jump into part 2. Overall, it's a pretty solid introduction to the world of deep learning for if you're a software engineer. It gives you just enough to keep you interested in both the theory, but also the practice behind it. It helps that it's in Python, right? So yeah, I would definitely recommend it. At some point, I'll probably go through these lectures again. Not sometime soon. Probably I have to go through. I don't know. Probably go through part 2 before I come back again to part 1 and part 2 again. I feel like this is one of those courses that maybe you do it once a year for like 2 years or 3 years to really solidify some foundations. But yeah, I do not regret having spent the time to go through these lectures, and I look forward to part 2 when I get around to it. I do want to quickly...
Hi, this is Jeremy Howard from Answer AI, coming to you here from
I've
Queensland,
heard about
Australia.
fast HTML, but I haven't tried it myself. I guess I could just go to the website. Impure button.
Hi, I'm Jeremy Howard.
Hi, I'm Jonna.
Hi, I'm Nate.
We wanted to give you a quick introduction here to Fast HTML. Have a look at some of these things that we made.
So this first example is a chatbot that I made to interact with ChatGPT. Mainly to try out a styling library for these beautiful looking chat bubbles. And this is the entire source code, there's no other components to it.
And this is an app that I made based off of Convey's Game of Life that allows multiple users to be able to play the Game of Life. And the backend, it uses WebSockets, and as you can see, the code is quite small.
Here's my little demo. It's maybe the most interesting one in some ways, but I like it because it's an example of like everything. It's Markdown, it's drag and drop, it's a complete custom login system, and that entire thing also fits onto a single screen of code written from scratch. Other people are making cool stuff with this as well. If you know a bit of web programming already, you'll get started real fast. Legendary author and web programmer Daniel Roy Greenfield said he would like to give it a try, and within 45 minutes of starting out with Fast HTML, he sent me a screenshot and said, look, I've just created a complete blog system. There's lots of great ways to create web applications nowadays. Data scientists in particular love these rapid dashboarding apps like Radio and Streamlit. What we've heard though, and what we found ourselves, is that when you're ready to go to the next level beyond your dashboard or proof of concept, things like this require rewriting from scratch in a totally different framework and learning a whole lot of new skills. Lots of people have created lots of fantastic web applications in Django. For example, Instagram is written in Django. But it's pretty complicated. This is the getting started setting up a new project example in less than 5 minutes. One great way to write web apps is with something like FastAPI on the back end and something like React or Svelte or Vue on the front end. You can create nice, sophisticated apps with this, but there's a lot to learn, particularly if you don't know JavaScript or TypeScript already, and then you've got a few other things to learn about as well. I've been writing web applications for years. I created the framework that Fastmail is built on. I started it over 25 years ago now. It's had millions of users. A lot of what I learned from that is now built into this. And ever since then, I've been looking for better and better ways to create web frameworks and to create web applications. I have hundreds of thousands of views of my tutorials on Flask, AngularJS, C#, and so forth. With FastHTML, this is by far the most excited I've ever been about web programming. I think it makes it so much easier, and I can't wait to see what you can do with it. So we're going to show you how to get started with building that to-do web application to create the source code that you see here.
Okay, so Jeremy, where's the rest of this? Can you show us how to create like the scaffolding and template that go along with this app?
There is no create scaffolding. There is no create fast HTML app. You just start typing into a window. That's all you do.
Wait, what about the front-end JavaScript code?
There is no front-end JavaScript code. You just type into one, Python file. Let's start typing the Python file right now. Jono, take it away.
Fantastic. Okay, so we're in a single Python file, and the app here is going to define some different routes that we can hit. So you could have different routes for different pages, for example, and here we're displaying some code and running the app. This has got something like live reloading switched on by default, so you can see all the changes that you make in real time. So whenever we build an app, we want to be able to show some content, but we don't have to type the HTML ourselves, we use templates. And so FastHTML has all of these built-in tags that we can use to construct the HTML programmatically in Python. Here we're creating a to-do list, the list, multiple items, and we're seeing if we can display that component. So we have this idea of nested components starting to merge here. We can create these with Python list comprehensions and so on, and start to build a UI. So let's add a form that lets us specify new to-dos, and then we need a way for these UI elements to interact with the app. So rather than going to whole new pages, what we're going to do here is use something called HTMX, which plays really nicely with FastHTML. Trigger an event, send a message to our server, and then we're going to have a new route that responds to that, in this case post request, asking us to add a new to-do. HTMX also lets you, doesn't refresh the whole thing, it just updates specific parts of it, so that's why we have the to-do list section here, and we're adding to the end of it any new to-dos that are added by that button.
All right, so let's add some persistency to this app. So you can use any sort of database, but already built into FastHTML is SQLite. So in our Fast app, we can set where our database is going to be stored and some of the fields, as well as which one's going to be the primary key. We can update our TD list to go ahead and go through all of the to-dos in our database. If we refresh that, we can see that it is returned, but it doesn't get added to the database. So let's go ahead and insert that. Now, as you can see, it's getting added. But we don't really render the returned post request HTML. So let's go ahead and add a little return function that makes it a little bit prettier. We can make this for the comprehension a little bit nicer. And as you can see, now we have a very beautiful rendering of the to-dos.
So from here, really, it's just about adding all the features you want. We've shown you all the key concepts you need to know. You know that you can use any HTML tag, but you can now create them as Python functions. You can compose them together to create component libraries for other people to use. You can use any CSS frameworks or web frameworks you like. So here, let's go ahead and add a delete link as well. So when you click on the delete link, it's going to call delete on the server. So create a function called delete and just go to to-dos.delete. We'll delete the ID that we're being passed. And now we've got delete tags. There they are. They're done. You can add anything from the entirety of the foundations of the web. So for example, you can add authentication by taking advantage of basic auth in your web browser. So now we've got an authenticated web app. We can add a logout by using your browser's logout functionality. So all of the functionality of the web is here for you to use. All of the components that exist, all of the web frameworks that exist, all of the CSS libraries that exist, they're now for you. And you can deploy it with a single line of code, and within a minute or so, it's done.
So we will be having a ton of fun writing examples. Do go check out our docs. We're going to keep adding more and more examples and documentation as we go, and I think you'll be able to get something that you can get started with, and we're really looking forward to seeing what you build.
Nice. Seems useful. Well, I'm sure it's useful. I'm not gonna claim that it's like, the new hot thing that everybody should build their apps with, but I'm sure it's there's a class of application for which this really works, especially for Python developers or data analysts or engineers who just want to have something quickly running. Interesting. Actually, that actually brings to mind, I know that we're building something internally, and I'm wondering why we did not give fast HTML a try. Hmm. Just trying to message somebody about this. Hmm. Okay, I think it's this one. Okay. Yeah, I think I'm just gonna call it for today's stream. Tomorrow and Thursday, the goal. We'll be doing some Kubernetes stuff. We're currently going through the official basics tutorial to get started, and that one is more. It's actually hands-on. You have to run commands and all that, so it's more interactive than what we've done with the long lectures of what we just finished, the practical deep learning stuff. So yeah, we'll focus on that for the next 2 days, and after that, next week when we pick up, when we resume work on deep learning stuff, it'll be, I think I'll have to do some research on something that I want to try out. During the stream, maybe there's a project that, just wanting to set up locally and try a bunch of things. They're always interesting, projects coming out. So being able to even just install them locally and run through a couple of examples is I think that's a good idea, just to be looking at it from a software engineering person who does not necessarily think of themselves as a AI data engineering person. Part of the reason why I'm also doing Kubernetes is because I strongly believe that infrastructure, at least understanding the having a solid understand as a software engineer what it looks like to work with these machine learning systems at scale requires having some being comfortable with some some concepts of just infrastructure stuff, and I think that's where the Kubernetes part comes in. I think if you were to do a survey of the biggest deployments of, machine learning models that are out there, I'm willing to bet that at least 75% of that rely on Kubernetes in some shape or other, especially the training part, the pre-processing of the data, the training, and just the way you set up your system to both optimize for throughput and latency. You obviously also want it to be reliable and fault tolerant. So these are, distributed systems ideas. You to build the systems, you need to, I guess to to be able to build some understanding of these systems, understanding how infrastructure works, understanding distributed systems concepts, scheduling, and all of that is important. So that's why that's why I've decided to do these streams. And yeah, the idea is to just keep going, and hopefully several months from now I'm still at it and getting better and better in my understanding of these machine learning models and systems, and finally have know enough about Kubernetes to be dangerous, but also at the same time know to love to hate it, I guess. So that's the goal. I'm also considering starting a series of videos on formal specification related stuff, specifically learning about TLA plus and other languages that are meant to be used for formal specification. But I mean, TLA plus tends to be the one that people recommend, I guess, starting with. I know it's one of the oldest ones. There are stuff that came out more recently, I would say. And I think the last one that I came across was called Quint. Where is it? No. GitHub, if I can type. Yeah, this Quint. It's one of the more recent attempts at providing a language that is more approachable than TLA plus. I've heard good things about it. Yeah, Quint is inspired by TLA plus. There's also there's Daphne. I think that comes from there's P. That's AWS, I think. There's P. There's Daphne. I think the guy who wrote Daphne is also at also works for AWS. I think this is one of the OG ones, if I'm not mistaken. the oh no, this is a library. F star is also, I think, one of the um, OGs in that category. Coq, which is a French name. I mean, it's a French word. Obviously, it doesn't sound very uh, good in English, but it's a French name. And I think there's even a petition to finally, wh- to, whether that's whether that's necessarily a good idea or not, I don't know. But there is a petition to change the name to something that's less well potentially problematic, uh, which kind of sucks if you're French, right? Because it's like now you're having to change the name of something that was named and made by, French people, but now you have to change it because, for adoption issues and the fact that, most of the world does speak English, and the word is kind of problematic in English. So, it is what it is. Yeah. And yeah, I think there are some projects in Rust. And there's Crosset. I think there's Canny. And I think there's another one. Is it this one? Anus? A verification toolchain for Rust programs. It might be this one. Yeah, so I think this is the one that I came across. I've already started, obviously. Fizby. Yeah, that's another one. That one is also okay. Now Quint is actually written in TypeScript. I don't know why I said it was Python. So Quint is in TypeScript. Yeah, mostly. And Fizby is in Python. Yeah. So yeah, a lot of these languages are just trying to provide a more friendly version of TLA plus. That I guess is more approachable to just software engineers who don't necessarily because TLA plus definitely I think it takes a mathematical approach to expressing the behavior of that's kind of the whole point of almost specification. A mathematical approach and temporal. There's a temporal aspect to things as well. So the syntax is not necessarily very friendly or familiar for the typical software engineer or programmer. So you see things like Fizby and Quint. I'm sure there are others. I think P as well is more in terms of syntax is closer to what programmers are familiar with. So yeah, I think this is what I came across a while back, and I was like, I would be interesting to go through this and get our hands dirty, just to understand some basics of what TLA plus is like. There's that for more specification. There's also a lecture that a series called Missing Semester of Your CS Education. Yeah, this. And I think it was originally taught by John Ginset. Is that his? Yeah. I don't know if I'm pronouncing that right. Genset or Gingset? Anyway, you get the point. He's pretty, I want to say prolific. Oh, okay, maybe not. He's known, how about we just say that? Known in the Rust community. He does pretty good. I don't know if you wouldn't necessarily label them tutorials, but more like walkthroughs. I think he has a series called Decrusting, where he basically picks some crates in a Rust community, like crates that are generally I guess popular and adopted by lots and lots and lots of projects, and basically goes through them and works through some code on how things are set up and why things work the way they do. I actually know he has he actually has a wow, actually, yeah, I didn't realize. Let me bookmark this. I don't know why I never cared to look up his blog. I only just watch his stuff on YouTube, and sometimes, yeah, like see his stuff on GitHub, but I never bothered to look up his actual blog, which I just found. Oh, and I'm pretty sure he wrote a book. I think it's called Rust for Rustations. But I'm not finding it here. But yeah, it's actually one of the books people recommend if you've gone through the initial barrier of getting into Rust, which I don't know why nobody ever recommended that to the Primogen, because I think the Primogen is on his second attempt at Rust stuff, and he's already given up on it again. And I feel like maybe if we tried this guy's book, maybe that could be the breakthrough. But yeah, anyway. This is actually an interesting. There are some. Uh-oh. I'm doing it again. Just opening tabs left and right. What is this? A high-level API for programmatically interacting with web pages through WebDriver. So this is like a Rust version of what's that? Playwright. Yeah, I mean, it seems like this is or at least a light version of playwright. Yeah. Anyway, how did we end up here? Wait, this is another thing that I opened. Okay, there are SQL schemas from your Rust struct definition to advanced trade system. Who's behind this? Somebody like, well, it's the same company, Helsing, and I think Helsing. Wait, Helsing AI. I bet you this is recent. It's so funny just watching how companies are somehow including the word AI somewhere in their branding. Um, yeah, I think housing is it's like the European version of Palantir. Excuse me. Yeah, that's my understanding. And they are supposedly um, the European version of um, Palantir. Buffer. Modern protobuf package management. I should save this. Just browsing. Just browsing. Right. How does this fit into UV? Oh. So, okay, so UV is a successor of this. Okay. Alright. Makes sense. Buffer. Well, did not store this? Yes, I did. Alright. There was another one that yeah, I think it was this one. Okay, so this is, you're using this to generate your schemas from your Rust types. So it's annotating the field as a primary key, a unique constraint. Sounds like a Postgres specific thing. Schema in the name. Relational stuff. Foreign key things. It uses SQLX underneath. Seems like. Okay, you have the pool. Then you can just do your CRUD thingies. Seems straightforward. Enter table. Operations. seems solid. I mean, they have some stuff to work on still, but I think it has the basic stuff. Anyway, okay, yeah, so yeah, I was saying how I wanted to dip my toes in some TLA plus. You know what, I should just go ahead and fork this. Maybe I should do that on Fridays. So Monday, Tuesday, we do deep learning stuff, AI stuff, and Wednesday, Thursday, Kubernetes, and Friday, TLA plus. I think that's a good lineup. Anyway, I think we've reached the end of the stream. Thank you for joining me or watching this at some point later. And yeah, I'll see you around.